This is the first section in the networks chapter, and it's all about trees. So first of all, what is a network? Well, at least in this case, a network we're going to call any connected graph or tree. And the nodes or terminals are the vertices. So think back to the other graph stuff we've done. Remember, we have vertices and edges. So yeah, vertices are nodes and terminals. Links are going to be the edges. So just some new vocab terms for stuff we've seen before. The theme of this chapter is finding an optimal network that connects a set of points. Okay, basic definition for a tree: a network with no circuits. A spanning tree is going to be a subgraph that connects all the vertices of the network and has no circuits. So we have one giant network, and we can take parts of that to create a spanning tree, and usually multiple spanning trees. The minimum spanning tree is, among all spanning trees of a weighted network, the one with the least total weight. So it's kind of like in the Euler and Hamilton circuits chapters, we're still trying to find the best value here and make things optimal. Trees are going to be a very applicable part of this course. It's a huge topic in computer science and something that programmers depend on heavily when creating programs and creating files and putting networks together. Alright, here's a simple example of a tree, just a family tree. Forrest, whose children are Nancy and Kim, and Nancy with children Craig, Barty, and Matt. Alright, another type of tree, it's like a vocabulary sorting tree. So we're sorting quadrilaterals here, something you may have done in a geometry class, where let's say you want to talk about a rhombus. Well, first of all, are there any parallel sides? Oops. Are there any parallel sides? Yes. How many pairs of parallel sides on a rhombus? Well, there are two. Okay. If there are one, we just have some kind of trapezoid. And if there are all the sides equal? If no, then we go to a parallelogram, but a rhombus would say yes. Are they at a right angle? If they were, we'd say a square, but no, that would create a rhombus. Another example of a tree, even a very small example actually, is a molecule C2H6 ethane. So if it may look familiar if you've taken chemistry. Another example here, let's say a couple decides to have children, and there's a possibility that they could have a boy or they could have a girl. And then maybe after, let's say they have the first boy, the first one's a boy, the second one could be a boy, or we could have a boy and then have a girl. Going over to the other side, we could say, all right, well, maybe the first baby is a girl, and the next child is a boy, or we have a girl the first time, and then the second time is a girl. And then going on to the third child, so the couple wants to have a third child, and say we've already had two boys, and we have a third boy, or we've had two boys, and they get a girl on the third child. Going over here, let's say they had a girl first time and then a boy second time. Well, they could have a boy the third time, making girl boy boy, or a girl boy the third time, making girl boy boy, or a girl the third time. So a girl, then a boy, then a girl. So just an illustration of all the possible outcomes in any binary kind of situation. All right. Here's one where we can break apart an order of operations question. So 4 plus 6 in parentheses times 8, subtract 4 halves. So this subtraction sign here is what kind of separates the two components of that problem, as you can see here. So and then the 4 plus 6 times 8, there's the two components there that get split off here, and then 4 divided by 2 gets split off here, and then the 4 plus 6 is kind of its own subcategory within this multiplication right here. And you can see that over here. Okay, so these are some examples of trees and non-trees. Earlier we said a tree is a network without circuits. So A, it looks pretty good. but not everything is connected, so it's not exactly a tree. B, we have a circuit right here, so that's not a tree. C, that looks like a tree, but it's not actually a tree because of the circuit. D looks even more like an actual tree, but remember, our trees, we're talking about math trees, not trees in nature. So this is definitely not a tree. We have 3 circuits right here. So that doesn't work. I'm not going to call that a tree in this chapter. E, that is a perfectly good tree. There are no circuits here. F, that's a good looking tree. Looks like we have a family tree over here in G. And this molecule here, or this compound, not really a chemist, I'm not sure what to call it, that is a perfectly good tree. Alright, a couple properties. In a tree, there is one and only one path joining any 2 vertices. If there is one and only one path joining any 2 vertices of a graph, then the graph must be a tree. So that's just the converse of the first statement. Property 2, in a tree, every edge is a bridge. If every edge of a graph is a bridge, then the graph must be a tree. In the, I think it was in the Euler chapter or the Hamilton chapter, we talked about in detail what a bridge was. Remember, a bridge is a piece that if you take it away, the graph becomes disconnected. So for example, if we were to take away this edge from Nancy, Forrest to Nancy, then that would disconnect the graph. So bridges are what we want when it comes to trees. Property 3. A tree with n number of vertices has n minus 1 edges. So we always have one less edge than the amount of vertices. If a network has n vertices and n minus 1 edges, then it must be a tree. So notice that there are 1, 2, 3, 4, 5, 6 edges, 6 vertices, 6 people on this tree, and then 1, 2, 3, 4, 5 edges. But we can't just go off that property 3 alone. Notice here that we have a disconnected graph, and this can have n vertices and n minus 1 edges. We have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 10 vertices, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. So it fits the criteria of property 3, but it doesn't follow property 1, where in a tree there's one and only one path joining any 2 vertices. So any 2 vertices we must be able to get from one vertex to the other. So if I wanted to get from J to H, I can't do that in this graph. So that's why this is not a complete network, therefore not a tree.